Section 1.5, page 5. The last piece to discuss in this section is called the intermediate value theorem, abbreviated with capital IVT. So suppose f is a continuous function. We've now just really solidified what a continuous function is, specifically on a closed interval between a and b. Then there is going to be some value n that is going to be between the outputs of f of a and f of b when f of a and f of b don't have the same output. Then there's going to exist some input number a that is in the open interval such that the function at that c value is going to give that in between. So we've got an in between output is going to come from an in between input, right? Notice a and b don't have equal heights, outputs, so there's got to be something in between them if they're not equal, and there's got to be a lot of points in between them if they're continuous. So we don't know where c is, but it's going to lead to some n output. Now the reason we want to talk about the intermediate value theorem is to show that there exists at least one root to any function. A root could also be called a zero or a solution. So we need to go through these steps to prove there is a root. First, we want to define the function. Sounds weird, but I'll explain why in a minute. Next, we want to verify that it's continuous. Then we'll need an x value that has an output that's negative and a different x value that has an output that is positive, right? Our two outputs are not equal to each other. Then there has to be an output in between them. In between all positive and negatives is 0. And therefore, we need to end with a concluding statement. Example 9 has x cubed plus 1 equals x is a function that could be graphed, and we need to show that it has a root, meaning somewhere this function passes through the x-axis. But notice we said we had to define the function first. The reason is a function is f of x, but this is not f of x, this is not f of x. So we need to subtract the x to the other side. Think of it as setting it equal to 0. So now I can use function notation to describe all of the terms I was originally given. I've defined a function. Now I need to verify it's continuous. So to verify it's continuous, it's just a polynomial, and we know all polynomials are continuous. We discussed that on an earlier page. So now I want to find an x value with a negative output. So I want f of x to be less than 0. Now let's look at the problem and be strategic. This is my equation. Because x cubed is the largest exponent, that's really going to drive what happens to this function. So I need a negative answer. Let's plug a negative into this piece. I just randomly start with -1. And when I plug -1 into the function, I got +1. I didn't get a negative. That's okay. That'll happen. It's not bad. It's how you get there. So I try the next negative number. And in this case, because I get 5, I've got that negative output. So when x equals -2, I have a negative output. Notice I'd gotten 1 as the output on the previous try. It was getting close to 0, so that's why I thought -2. If this had been 100, I probably would have tried like -20. Now I need to get a positive output. We just got a positive output. It was our mistake in step 3. So really another reason it wasn't a mistake. So now I know an x value that is going to have a positive output. So therefore I can say by the intermediate value theorem, there must be a root in the interval of the two values that I found. Now this was just me kind of thinking as a graph. I've got -2 and I got a negative output. I got -1 with a positive output. So somewhere this graph had to cross the x-axis. If you used a graphing calculator or some sort of graphing site like Desmos, you would see this is what the picture actually looks like. And sure enough, in between -2 and -1, I'm going to have a solution or a result. Keep in mind, maybe you started with -5 and -1. That would be fine, just stating that therefore by the intermediate value theorem.